everyone. Thank you so much for joining our webinar today. I'm Anya. I'm part of K-Mine Business Development team. And while we're starting, I'd love for you to follow our LinkedIn page where we drop all of the updates and information on upcoming webinars. So today we're exploring 5 actionable steps to ensure a stable open pit. We'll cover cost-effective ground control techniques and rapid response strategies to keep your operations safe and efficient. But before we dive in, let me give you a quick intro to K-Mine. We started our company in 1994 in Ukraine, and since then we expanded our reach across Europe, United States, and Canada. And our team is a talented mix of developers, geologists, mining engineers, many of whom are qualified for NI 43-101 and JORC reporting standards. And we work with all type of clients, from small exploration crews to big corporations, providing high quality and cost-effective solutions tailored to their needs. So let me tell you a bit about what we do with K-Mine. We created a software built specifically for the mining industry, covering everything from late exploration to production. Our toolkit includes flexible models that work smoothly for both open pit and underground mining. And what sets us apart is how adaptable our solution is. Whether you're running a small operation or managing a large company, you can pick and choose the models that fit your needs. Start with just one or go for the full package. These models handle key tasks like managing geological data or crafting optimized mining plans, like short-term or long-term. Plus, our software integrates with IoT devices and dispatch systems, giving you a real-time monitoring to stay on top of everything. Our software at K-Mine comes straight from hands-on industry experience, built to tackle the real challenges we've seen through our consultancy work. As I mentioned earlier, our team includes qualified persons who produce reports meeting NI 43-101, SK 1300, and JORC standards customized for project stages like pre-feasibility, feasibility study, mineral resource estimation, and others. So we bring deep expertise across a wide range of hard commodities. And if you're curious about how our services can help your project, drop a comment below or shoot us a message through the contact form on our website. So today's webinar is designed to equip participants with well-rounded understanding of how effectively manage geotechnical risks in mining operations. We'll start by identifying the most critical geotechnical risks, helping you recognize early warning signs before they escalate. Then we'll cover the essentials of geotechnical data collection, emphasizing best practices and common pitfalls to avoid. And moving into practical application, we'll introduce tools and techniques for risk assessment that are both reliable and efficient. And to help keep operations safe and budgets in check, we'll also explore cost-effective ground control measures that don't compromise on performance. And finally, we'll wrap up with a rapid response strategies so you're prepared to act decisively and effectively when the unexpected happens. So let's first get our definition straight. A geotechnical risk is the probability of an unfavorable event occurring within soil or rock masses which could cause damage to structures or harm to people. Simply put, it refers to dangers associated with unstable ground conditions, be it landslide on a slope, sudden ground settlement, or collapse of a pit wall. So the first step is to have a stable pit is to understand what your geotechnical risks are. If such risks are not defined in advance, the consequences can be severe, ranging from operational downtime to full-blown accidents and threats to human life. That's why a geotechnical engineer's first task is to identify the key risks at the early stage of a project or during site operations. So geotechnical risks come in so many forms, but some of the most common include slope instability, such as landslides or slope failures on natural terrains and pit walls. For example, a pit wall in an open pit mine could collapse, threatening equipment and personnel below. Another significant risk is ground subsidence or settlement, often caused by erosion of subsurface materials like karst cavities, underground workings, or weak soil beneath infrastructure. Ground-related risks are also critical. Rising water levels or flooding can weaken soil and trigger slope failures or loss of bearing capacity. Seismic activity must also be considered, especially in regions prone to earthquakes, which can disrupt slope stability. And these risks are particularly relevant to the mining industry. So, to effectively manage risks, they first must be recognized. Identifying geotechnical risks involves gathering all available information about the site and pinpointing potentially problematic areas. In practice, this means first studying the site's history. Have there been previous landslides, slope collapses, or settlement events? Past experience often highlight weak spots, and then engineers conduct visual inspections. Typically, experienced geotechnical specialists can spot early warning signs like slope cracking, leaning trees, or bulging soil. And third, cartographic data must come into play, like geological maps, slope gradient maps. Hydrogeological surveys help reveal weak materials, steep inclines, faults, or areas with high water tables. For instance, a map showing clay layers outcropping on a slope may indicate a potential landslide zone during wet conditions. Finally, all identified risks are documented in a risk register, where each risk is described with its likely causes and potential consequences, and this structured approach ensures that no threat goes unnoticed. So, what improves the quality of risk identification? So, of course, first of all, it's teamwork and then digital technologies. Geotechnical engineers must work closely with geologists, surveyors, environmental specialists. Each contributes data to the overall picture. Early stage geotechnical monitoring also plays a key role, like installing simple visual markers or conducting periodic surveys of slopes can also help detect early ground movements before it becomes hazardous. And nowadays, advanced tools are also available. For example, specialized software solutions can rapidly assess slope stability and highlight areas of concern. In K-Mine, for example, there is a dedicated slope stability analysis module that integrates cross-sectional data, fracture information, soil properties, and generates a risk map highlighting potentially unstable areas. So engineer sees clear picture. Here, the factor of safety is low, indicating a possible slide. There, conditions are stable. And these technologies support the expert's judgment with objective computational insights. So a risk identified earlier is a risk half managed. Knowing potential problem areas from the start lets us design proactive solutions. Once we define what and where the threats are, we can move to the next step, step number 2, collecting data for quantitative risk assessment and planning mitigation measures. So basically, we just need to know what our soils and rocks consist of, how strong they are, whether water is present, and how the ground behaves under stress. So quality data collection in this case is the basis of accurate analysis, and mistakes and negligence during site investigations can compromise all subsequent stability calculations. That's why geotechnical investigations are performed as thoroughly as possible. They typically include field inspections, borehole drilling, sample collection, lab testing, groundwater level management, and more. The goal is to build an objective understanding of the site's geological structure and soil mass characteristics. One of the key methods is geotechnical drilling. Boreholes are drilled at predetermined locations to look beneath the surface. From these boreholes, rock or soil samples are extracted. It's core samples in case of rock, and undistributed samples for soft soils, which are then sent to a lab for testing. The geologist assesses core samples to determine lithology, layering, fracture density, and overall rock mass quality. In softer soils, hollow stem auger drilling is used to obtain intact samples. In parallel, field tests are also conducted, like cone penetration testing is widely used, where cone is pushed into the ground while measuring resistance. And this method estimates soil density and strength without the need for sampling. In rock masses, field strength testing is essential, and for example, using a pressure meter for in situ loading or wind shear test for clays. These methods yield key parameters like internal friction angle, cohesion, deformation modulus, and other essential values for stability calculation. In addition to drilling, in situ observations play a crucial role. When working with pit slopes or exposed rock outcrops, geotechnical engineers often carry a structural mapping, and this means describing the visible rock layer and identifying fractures, measuring their orientation, and looking for signs of weathering. To evaluate the quality of the rock, they use tools like rock quality designation or RQD, which means the percentage of solid and unbroken core recovered. Systems like RMR or Q also help assigning scores based on the factors such as rock strength, fractures conditions, water presence. It all gives an overall picture of rock mass quality. These field observations are frequently supported by geophysical surveys, such as seismic testing or ground penetrating radar. And these methods help detect what's going on below the surface, things like faults, weak zones, or underground cavities. And geophysics are particularly viable in areas where drilling isn't practical or is too expensive. So, as data accumulates, the next challenge is to properly document and analyze it. Field investigation results are typically compiled into a borehole logs and geological maps, table of soil properties, and lab reports. And it's essential that all of this information be securely stored and easily accessible to everyone involved in the project. Increasingly, digital databases and 3D models are being used for this purpose. For example, geologists construct a three-dimensional model of the stratigraphy based on the drilling results. This model forms the basis of a geotechnical model where each unit, layer, or block is assigned properties like density, strength, internal friction angle. The advantage of such a model is that it can be used directly in numerical analysis software, for example, like K-Mine. It allows all geological and geotechnical data to be stored within a single database. That means that the investigation data can be passed directly to slope stability modules and other specialists without loss or distortion. Geotechnical engineers gain the ability to quickly update the model. For example, if new boreholes reveal a weak layer, it can be added to the model and the slope calculations can be rerun immediately. In this way, high quality and well-interpreted data forms the foundation for accurate analysis. And with a good understanding of soil composition and potential weak zones, the next step, we can begin the slope stability analysis. The purpose of this analysis is to predict whether a slope will remain stable or collapse under given conditions. A standard indicator used in such assessments is the factor of safety, which is the ratio resisting forces like soil strength, shear resistance to driving forces like gravity, load, water pressure, etc. If the factor of safety is below 1, the resisting forces are insufficient and the slope will most likely collapse. The value near 1 indicates marginal stability, where even small disturbances could trigger a landslide. To ensure adequate safety, projects usually require a factor of safety above certain threshold. Usually it's about 1.2 to 1.3 for permanent slopes and about 1.1 for temporary ones. Depending on standards and risk levels, stability analysis also is used to calculate this ratio under various conditions to determine whether a slope is safe. This method chosen for the analysis depends on the complexity of geology and the design phase. Simple cases may be analyzed with empirical formulas, while more complex situations require numerical modeling. So there are several ways to assess slope stability. The simplest are empirical and analytical methods based on engineering experience. In some cases, an engineer can estimate the allowable slope angle using analogs and reference data. For example, for loose field soils, published guidelines define maximum unreinforced slopes. Typically, it's around 34 to 37 degrees for dry, dense sand. For rock masses, empirical criteria rely on mass classification systems. If the rock is strong and massive, meaning it has high RMR, steeper slopes can be used. If it's weak and fractured, the gentler angle is recommended. These empirical approaches are useful during preliminary design. They offer a quick grasp of conditions, but they don't account for all variables. So as a result, they're usually followed by more precise calculations that consider site-specific parameters. Still, such initial estimates help engineers make early decisions and prioritize areas for more detailed analysis. Limit equilibrium methods, or LEM, are the geotechnical engineer's primary tool for slope stability calculations. The concept involves assuming a potential slip surface, for example, circular arc in homogeneous soils, or planar surface along a weak layer of fracture in rock. These methods then calculate the balance of forces acting along the surface. Resistant forces like a mass of stable soil, shear strength, cohesion versus driving forces like weight of the unstable portion, water pressure, seismic forces, etc. Classical LEM techniques, such as those by Fillenius or Bishop, differ in mathematical assumption, but they arrive at the same goal, computing the factor of safety. For rock slopes, specialized schemes apply, like wedge failure or planar sliding analysis. In case of wedge failure, a block is bounded by two intersecting fractures, and in case of planar sliding, the mass slips along a single inclined plane, for example, weak bedding layer. And K-Mine can automatically iterate through multiple possible slip surfaces to find the most critical one with the lowest safety factor. And this dramatically simplifies the engineer tasks, enabling rapid analysis of complex slopes, which includes multiple soil layers and water conditions. Another level of analysis involves numerical modeling using finite element or finite difference methods. Unlike limit equilibrium, which assumes a predefined failure surface, numerical methods simulate stress and deformation throughout the entire soil or rock mass. The finite element method, or FEM, is especially valuable for complex conditions such as nonlinear soil behavior, irregular slope geometries, or stage construction. FEM also divides the slope into a mesh of elements and solves equilibrium equations for each, producing detailed visualizations of stress distribution, displacement, and failure zones. Engineers can see not only the factor of safety, but also where plastic zones are forming, how much settlement will occur, and where tension cracks may develop. Such analysis is available in K-Mine or other specialized packages like Plaxis, which integrates seamlessly with geological models. In addition to static calculations, specific external factors often need to be accounted for. In seismic regions, slope stability is evaluated under earthquake conditions using pseudostatic methods, typically by applying an equivalent horizontal acceleration. Rainfall or climate factors also play a role. Prolonged precipitation, for example, can saturate slopes and reduce soil strength, so analysis must include moisture sensitivity. Another important dimension is probabilistic analysis. Since soil properties are never known with absolute precision, engineers must ask, okay, so what if the soil is weaker or the load is higher than assumed? Probabilistic methods such as Monte Carlo simulations allow for input parameters variability and estimate probability of failure. If the likelihood of slope failure is significant, this indicates the need for additional reinforcement. While such advanced approaches are less common in everyday practice, interest in them is growing, especially for high-risk or sensitive projects. The result of stability analysis is just it's not just a number, it leads to practical recommendations. Based on the analysis, geotechnical engineers determine whether a slope is stable and under what conditions it might fail. If the safety factor is insufficient, stabilization measures are proposed, and that's something we'll cover next. But it's important to stress that any calculation result it must be interpreted critically. A model is a simplification of reality, even a good model. So engineering judgment is essential. Comparing different approaches also adds confidence. For example, if both limit equilibrium and FEM produce similar safety factors, the results are likely reliable. But if they differ greatly, it's something might be wrong. So in today's environment where powerful software is available, the real challenge is to framing the right problem and thoughtfully interpreting results. By combining various analysis methods and using monitoring data, engineers can achieve accurate assessments and develop targeted mitigation strategies. So once the analysis is complete, we understand whether the slopes are stable. If calculations show low safety margins or ground movement is detected, is considered reinforcement as the next step. However, expensive retaining walls or deep anchors may not always be necessary or even feasible. Often, simpler and most cost-effective solutions can significantly enhance slope stability. These measures don't rely on rare materials or complex technologies, but rather smart engineering decisions and, of course, available resources. So let's look at the approaches that offer a noticeable improvement in slope stability without major capital investment. Well, first, and often most effective measure is water control. As I mentioned earlier, water greatly reduces soil strength, so it must be kept away from slopes. Drainage measures can be very straightforward. For example, excavating ditches or channels to divert rain and meltwater from the slope crest, or installing drainage blankets or perforated pipes within the slope to reduce groundwater levels. And in open pit mines or waste dumps, the longitudinal ditches are often installed along berms to prevent erosion and saturation. Where possible, the water table is lowered by cutting a trench at the slope toe or by pumping water from wells. These methods are relatively inexpensive, especially when compared to the cost of full-scale slope collapse. Another approach is geometrical reshaping of the slope. This essentially means flattening the slope by redistributing material, and the most drastic method is to reduce the slope angle, cutting down from the top or adding fill at the bottom. While full regrading isn't possible, benches and berms can be added to break the height into smaller segments, shortening the potential slip surface and trapping falling debris. And even minor changes help. Relocating heavy equipment away from the slope crest or removing excess material from the top reduces driving forces. These earthwork-based solutions typically require only excavators or bulldozers, tools that are available on most sites and much cheaper than large engineering structures. So you can see on the video the process of determining the optimal pit slope angle using the combination of finite element method and the limit equilibrium method. The analysis begins with evaluating the stress distribution and identifying the geological and operational constraints. And based on these inputs, inverse approach is applied to calculate the slope angle that yields the highest factor of safety. The next step of measures focuses on surface protection and minor reinforcement to prevent soil loss, manage small slips, and slightly enhance soil stability. One cost-effective approach is simply slope vegetation. Planting grass or shrubs anchors the surface with roots, reducing soil erosion. And while it's not sufficient for deep-seated failures, vegetation effectively curbs the surface degradation. To aid plant establishment on steep slopes, biomats made of coconut fiber or synthetic mesh secure seeds and soil until roots take hold. And for tougher conditions, geosynthetics like geogrids or geotextiles are employed. Geogrids laid across the slope filled with soil and gravel create a mechanical interlock, and geotextiles act as reinforcement and separating layers, boosting slope resilience, particularly in field slopes. So on rock slopes, options of course are limited, but wire mesh anchored to the surface is a common economical choice to prevent minor rock falls. And collectively, these surface techniques mitigate small-scale slopes issues that can lay the groundwork for more substantial solutions if required. And finally, let's consider localized reinforcement structures that can be relatively affordable. Gabions, for example, mesh box filled with rocks. It's a great example. They can be built into retaining walls at the slope toe. The rock can be sourced on site, for example, from waste rock, and the mesh is inexpensive, so result is a strong, permeable structure that stabilizes and drains the slope. Another option is soil nails, slender steel bars driven or drilled into the slope at an angle, and they bond with soil resistant movement and are cheaper and easier to install than large anchors and piles. For temporary stabilization, even simple measures help. For example, covering the slope with plastic sheeting before heavy rainfall to prevent washouts. So individually, these methods may not solve large-scale problems, but together they can definitely meaningfully boost slope stability or buy time until permanent solutions are implemented. These low-cost measures are especially effective when used proactively. It's much easier and cheaper to implement drainage and slope grading earlier than to deal with major landslide afterward. Of course, some situations call for significant investments like anchors, piles, or heavy retaining walls, but for many small projects or, for example, early stage operations, simple interventions are enough to maintain accessible safety levels. The key is choosing the right solution for each, and effectiveness is verified through recalculating the safety factors like in K-Mine or another platform. And if the target factor of safety is achieved, the solution is validated. Using low-cost enforcement, engineers can reduce failure risk and significantly without excessive expenses. However, incidents happened, and it's critical to know what to do if a slope starts to fail or collapses suddenly. Rapid response means taking immediate action to minimize consequences and prevent escalations. Sometimes every minute counts, especially when lives are at stake. A well-developed emergency response plan ensures no time is lost. Such plan usually includes identification protocols, evacuation procedures, hazard zone cordons, and responsibilities for responders. And so a key element of the rapid response is monitoring and early warning. Identifying abnormal ground behavior in time can turn a potential disaster into a manageable incident. Modern technologies are extremely helpful in that, by the way. Many open pit mines now use radar systems that continuously scan pit walls and can detect millimeter scale movement long before collapse. If movement accelerates past a threshold, an alarm is triggered, providing time to evacuate people and equipment. And besides radar, instruments like extensometers, inclinometers, and GPS markers feed real-time data into central systems. Integration here is the key. A control center running dedicated software receives and processes data, and the digital geotechnical systems links with IoT sensors, for example, in case of K-Mine, integrated with field devices, automatically analyzes readings and notifies engineers of threshold breaches. When alarm sounds, whether triggered by monitoring or an actual collapse, the first response always must be automatic. Safety comes first. Evacuate everyone from the danger zone immediately. Operation stops. Equipment is shut down. Personnel is moved to safety. If the incident occurs in public infrastructure, for example, a landslide threatening a road or community, emergency services must be called, road blocked, and residents warned. So the response must be calm but swift. Lives matter more than machines. And once people are safe, the immediate danger is reduced. It's time to stabilize the site and mitigate further risks. The situation must be assessed. Okay, how much material was displaced? What infrastructure was damaged? And where the additional collapses are likely? Often the slope remains unstable right after a failure, so inspections must be also cautious. Drones are highly useful here, providing aerial imagery or 3D models of the failed area without putting personnel in danger. Based on the assessment, urgent measures must be taken, collapsing an overhanging block in a controlled way or quickly draining a saturated slope. Meanwhile, of course, cleanup begins, clearing debris from roads, restoring access, or stabilizing areas critical for safety. A crucial part of emergency response is communication. Internally, roles and responsibilities must be clearly defined. Externally, transparency is essential to avoid panic and misinformation. But quick response doesn't end with solving the immediate problem. Every incident is a learning opportunity. So afterward, the team must analyze, okay, were there missed warning signs? Did the monitoring system work effectively? Were resources adequate? Based on these lessons, the response plan is updated, the risk register is revised, and the entire risk management cycle begins again with new insights. So, by reacting effectively and learning from every event, a company can strengthen its geotechnical safety. So, in conclusion, geotechnical risk management in open pit mining is a multi-step process, and we begin by identifying hazardous zones, gather detailed data on soils and conditions, analyze slope stability using the right tools, implement cost-effective stabilization where needed, and stay ready to act if emergencies arise. A comprehensive and proactive approach significantly reduces the likelihood of disasters, and when things go south, it ensures that we are prepared. So, smart risk management may not eliminate uncertainty, but it certainly gives us confidence and control. And that's it for today. Thank you so much for joining our webinar, and I'll see you next time.